We've already talked extensively about intermolecular forces in liquids. Dipole-dipole forces, ion dipole, induced dipole, London forces, and hydrogen bonding. Those type of forces are specific to liquids, and when we start dealing with solids, we have different intermolecular forces. Those forces actually create solids in different arrangements, and our job today is going to be to classify those solids based on the intermolecular forces that are present. We have two main types of solids that we're going to look at. We have crystalline solids. These are crystals. These are quartz, rubies, sapphires, diamonds, things that make crystals with organized arrangements of particles with distinct shapes. Pretty much, in fact, any type of gemstone is a crystalline solid. We have amorphous solids, which are indistinct. They can be molded, they can be shaped into whatever means we need them. Glass can be melted down into sheets, into cups, into many other different things. Same with rubber. When we start looking specifically at crystalline solids, we have five main types. Atomic solids, these ones, as the name would suggest, are formed from atoms, mostly covalent bonded molecules. Molecular fits under that category as well. Network solids are other covalent molecules, and we'll see atomic, molecular, and network all being covalent molecules. They are very similar, but they do have some differences. Ionic solids, those are ionically bonded compounds. And metallic solids, as the name would suggest, those are made from metals. So the atomic solids, individual atoms held together by dispersion forces, by London forces only. So if we're going to talk about an atomic solid, it would have to be something that is just held by London forces, and in nature, the only atomic solids are the noble gases, helium, neon, etc. These type of solids have very low melting and boiling points because London forces are the only things that hold them together. Those are very weak forces, so it doesn't take a lot of energy to overcome them. Similar to atomic solids, but slightly different, the molecular solids, these are made up of molecules. These are held together mainly by dispersion forces. They have low melting and boiling points as well. Now we can have polar molecular solids with some dipole-dipole forces, possible hydrogen bonding as well. These are still molecular solids, but the intermolecular forces holding them together are somewhat stronger, so they have higher melting points and higher boiling points than nonpolar solids. Just to give you an example, propane, a nonpolar molecular solid, melts at negative 190 degrees Celsius. A similar sized solid, formic acid, this is a polar molecule. It has a melting point of 8.4 degrees Celsius. This is because formic acid has some dipole-dipole forces involved with it, where propane only has London forces. Network solids are somewhat different than the molecular solids. These ones have networks that are bonded into three-dimensional arrays. So I have a diagram shown of graphite. Graphite is what's used in pencils. It's soft. It's a two-dimensional network solid. And the way we know it's a network solid is each of the individual carbon atoms that make up graphite is bonded to another carbon atom. Three covalent bonds, but we know carbon has 4 valence electrons. The fourth pair of electrons, and this is a new concept, it's delocalized, meaning that fourth pair of electrons kind of floats throughout the solid everywhere. The layers, individual layers, are held together by dispersion forces, but we have covalent bonding in each layer. So we have two different things going on here. Each layer is held together by covalent bonds, but layer to layer, like so, is only London forces. So because of that difference, the layers of graphite are able to slip over the top of each other, and which makes it very good for use in a pencil, where some of the graphite needs to slip off onto the paper and some needs to stay on the pencil. In a lot of industrial processes, high-end machining, graphite is used as a lubricant because it slides off of itself really easily. Why graphite and not oil? Well, because graphite is much easier to clean up. Oil is messy, sticky, whereas the graphite, it takes a little bit of compressed air to blow it off, and it's all cleaned. Diamond, we have the same kind of thing. This is again a network solid, except now that fourth pair of electrons is actually bonded to another carbon atom. Another type of carbon compound is called a fullerene. This is a special arrangement where a number of carbon atoms come together and they form often a ball. If you look at the diagram, this is C60. It was discovered in 1985. The name of it is Buckminster fullerene, commonly called a buckyball. No, I'm not kidding, that is the actual name. Why is it called a Buckminster fullerene? Because in the 1800s, there was an architect named Buckminster Fuller, and he designed structures that had actually the same shape as this carbon. This is just one carbon buckyball. We have C70, which makes a ball, C74, C82, and there are many more as well. Now, because these carbon allotropes have a spherical shape, the proposition is they make good lubricants. Why don't we know this for sure? Because these are very difficult and very expensive to produce, at this point they don't make a lot of sense to use as a lubricant. Whereas graphite, on the other hand, very easy to produce, cheap, readily available. That's why it gets used. As well, a lot of research has gone into making what's called nanotubes out of carbon. Now, a nanotube is just a very, very small cylinder, and the diagram kind of illustrates that. Imagine that that's just a test tube laid on its side with the walls made out of carbon. We've made nanotubes out of C400, that's 400 atoms of carbon bonded together. It's been used to make some high-strength fiber. The diameter of that fiber was 4 times 10 to the negative 8 meters. That is less than 1 micrometer. So all of these carbon solids have been network solids, but we can also have other compounds that are network solids that are not made out of carbon. Silicon dioxide, SiO2, as shown in the diagram, is a network solid. Silica as well. Many of you with cats will be familiar with silica. It's the little white crystals that you put in to minimize the odor. Pretty much, if you want to know if something is a network solid, most carbon compounds and a lot of silicon compounds are network solids. The reason that carbon and silicon make good network solids is because of their outer shell electrons. Carbon and silicon all have 4 valence electrons, meaning each carbon or silicon atom can bond to 4 other elements. By allowing 4 bonds, it's easier to create a network than, say, fluorine, which is only able to bond to one other element. We can talk about ionic crystals. These are essentially network solids as well, but they're made of ionic compounds. We don't call them network solids because network solids are devoted to the carbon and silicon compounds, but ionic solids are very common as well. Why do ionic solids form what's called a crystal lattice? Because of the size of the ions. What we have here is each unit cell, that is the brown square, that would be one molecule of, let's say, sodium chloride. Underneath that would be another molecule of sodium chloride. Behind that, and the same thing. These form the network because of the size, like I said, and think of it this way. If we have two different types of fruit, let's say grapefruits and kiwis, large fruit and a small fruit, we can fit quite a few kiwis in the gaps formed by the grapefruits. That's exactly what is going on with these ionic networks. The large cations and the small anions leave space between them. And as we can see over here, we have very large chlorine ions, and smaller sodium ions that fit very nicely together. This picture on the right is a cutout of what it would look like, but because of the sizing, those atoms fit very closely together. So what do we have right now? We have atomic solids, which are made solely of atoms. Where would we find them? Group 18, those are the noble gases, helium, neon, etc. Those are the only types of atomic solids we're going to see. Molecular solids, these are made of either nonpolar or polar molecules, essentially the covalently bonded molecules. Some covalent molecules are polar and some are not. The network solids, these are things like graphite, diamond, silicon dioxide, usually carbon and silicon-based compounds. We've talked about ionic solids. These are made out of ionic compounds as opposed to molecular, which are covalent or polar covalent. Some examples: sodium chloride, calcium fluoride, etc., etc. The last piece that I haven't talked about yet is the metallic solids. These ones are incredibly easy to tell because they are made of specifically metals only. So pure mercury, pure copper, and so on and so on. Those are the 5 types of crystalline solids. The other type of solid we have is the amorphous solid. These type of solids don't have any strict order to them. They are free to flow as they want. So glass is the most typical amorphous solid. What happens in the making of glass? Limestone, soda ash, and silica sand. So quite literally, sand you could find on the beach, limestone that is mined all over Canada, and soda ash, sodium carbonate, is heated up to 1700 degrees Celsius, where it all melts, cools down, usually on a slow, controlled process to control the shape, and it forms glass. Now, we can add different compounds to the glass, such as silicon dioxide, sodium oxide, calcium oxide, magnesium oxide, and aluminum oxide. Those would change the color, change the pliability, change the strength of the glass, and so on. So if we want green glass, we might add a copper oxide compound. If we want a more flexible glass, we might add a different compound to it. Very easy to change the properties of the glass. If we add boron oxide, 13% of the weight of the glass becoming boron oxide, we get what's called borosilicate glass, commonly known as Pyrex. I'm sure most people have some Pyrex glass in their kitchen. What Pyrex glass does is, because of that boron oxide, it expands very little when it's heated. So it can be put in the oven, or it can be put in the microwave, or the dishwasher. That type of glass does not expand or contract when it's heated. It's also somewhat more flexible, meaning that it can withstand the repeated heating and cooling without cracking and breaking. It's not 100% foolproof. I have had Pyrex smash on me, possibly because of the quality when it was made, possibly because it was just used so much that it eventually did give out. If we add lead 2 oxide to the glass, it's called flint glass. That flint glass is actually used in glasses, eyeglasses that is. The benefit to that is the light doesn't bend very much when it goes through flint glass, and for most people their eyesight is close enough. They only need the light to bend a little bit, so that gives a little bit of extra control. Now, glass is not the only amorphous solid. Charcoal, same type of stuff that many people put in their barbecue. Sulfur, when it's heated to boiling and cooled quickly, we get something called plastic sulfur. It is still sulfur, but it's got the texture of plastic. So now that we've gone through all these different types of solids, we need to be able to classify them. We have 5 different classifications we're going to look at. I'm not putting atomic solids on here because we're not going to be dealing with those. Those are only the noble gases. So P4O10. We can right away cross off ionic solids because this is not made of ions. It's not metallic either because it's not a pure metal. It's not a network solid because it's not made of silicon or carbon compounds, and it's not amorphous because it's not glass or plastic or the like. P4O10 is a molecular solid. B, NH43PO4, ammonium phosphate. It is not metallic. It's not network. It's not amorphous. So that leaves us with either ionic or molecular. Well, this in fact is an ionic solid because it's made of 2 ions. As you would remember from Physical Science 20, NH4 is ammonium, PO4 is phosphate. That makes an ionic compound, ammonium phosphate. SiC, silicon carbide. This one has the double whammy of having both silicon and carbon in it. This is definitely a network solid. I2, not ionic. We don't have different ions. Not metallic because iodine is not a metal. It's not network because it's not made of silicon and carbon atoms, and it's not amorphous, so this must be a molecular solid. We have the same situation with P4. This is another molecular solid, so we can just classify that without going through the last half. Plastic. Plastic is like glass. Plastic can be melted, bent, shaped how we want. It does not have a discrete shape. Plastic is an amorphous solid. Graphite we've already talked about. Graphite is the classic example of the network solid. Brass is just an alloy or a combination of different metals, so it is in fact a metallic solid. Rubidium fits in the same category as brass. It is a pure metal. It's a metallic solid. Lithium bromide, going through, it's not metallic because it's not a pure metal. It's not molecular because it's not made of molecules. It's not a network solid, no silicon or carbon atoms to be found. It's not amorphous because it does have a shape. It's an ionic solid. Last but not least, silicon. This could actually be categorized in two ways. We could call it a molecular solid because it is just one type of atom, or we could call it a network solid because it is silicon. Either or would be correct, but the more correct one is that it is a network solid.